number 19. Oh, I'm going to talk about 17 quick. We were looking at the goldfish. For this one, there were 13. And so you're going to have a permutation of 13, choose 5, which is 13 factorial over 13 minus 5 factorial. 13 factorial over 9 factorial. Okay, that's how we chose the goldfish. With slots, there were 5 slots. There were 13, then 12, then 11, then 10, then 9. Multiply those together, you get 13 factorial over 9 factorial. For the car one, a car holds 3 people, okay? In the front seat, 3 people in the front seat, okay? And 4 in the back. That's the way the old cars were. My first car was a Plymouth Fury 3. Do you know who Stephen King is? One of his famous books was Christine, the Car That Kills. And I had that car. It was my very first car. And I drove it for 6 months. And I found out after 6 months there was a leak in the exhaust coming into the cab. And if I would have kept driving it, it would have killed me. But anyway, it has nothing to do with this problem. But in the front seat, the same person is always driving. Okay? And then in the back seat, John and Samantha are anywhere back there. I don't know where. They're not in any particular. They're not sitting together. They're just in the back. So probably what you want to do is with these 3 people designated, how many people are there that could sit in this seat up here? 4. There's 4 left. And then how many could sit in this seat? 3. Then how many people are there for the back? 4 people. Then 3. Then 2. Then 1. Since those 2 don't have to sit there, so the answer to this is going to be 4 times 3 times 4 factorial, which is going to be 12 times 24, which is 144 times 2, which is 288. Is that what they had in the back? Okay. Okay, front seat has 3 people. Front seat has 3, and the back seat has 4. And it says there's only 1 driver, so 1 person is out of the mix right now. They have to drive. It's their car. Then John and Samantha are 2 people that have to sit in the back. So there's only a total of 4 people in the front that you can pick from. And then there'll be only 3 people that could sit in the front. Okay, so now there's, other than John and Samantha, there's only 2 people left. But when you take the back seat, there's a total of John, Samantha, plus 2 people that can sit in the back. So that's 4 people, and they can sit anywhere they want. 4, 3, 2, 1. So that's why I've got this 12 times 4 factorial. Good question. How about another one? Any other ones you want to see? All right, 23 is a circle table, and it says how many ways can 4 women and 3 men be arranged in a circle? So how many total people are there? Well, there's 4 women, A, B, C, D, and there's 3 men, A, B, C. So how many can they go in a circle? We talked about this. There's 7 people, but in a circle, you just subtract 1 to get 6 factorial. Are you okay with that? Okay. Then it says, how many ways can this be done if the tallest woman and the shortest man have to sit next to each other? Okay. So I look at it this way. How many units are there now? There's 1, 2, 3, 4, 5, 6 units. And so then it's just going to be 6 minus 1 factorial. But what else do we have to include? Why is that, Trevor? Yeah, these can switch places, AD and DA. So we're going to multiply by 2. So this is interesting. This is 6 factorial. This is going to be 5 factorial times 2 for the circles. Any others on this problem set? You doing okay with the Venn diagrams? 4? This one? Yeah, good review. So for number 4 Venn diagram, the events A and B are such that this is A and this is B. All of the probabilities add up to 1. So the probability of A is 0.5. The probability of B is 0.7. But they are super kind to you, saying that, what does that upside down U mean? Intersection, yeah. Okay, so A intersect B is this part here, 0.2. They don't give that to you most of the time. Most of the time, you're going to have to use the fact that the probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. Because A and B would include this twice. So you subtract one of the intersections. So this is a way that we can find intersections if we know union A and B. Well, that's not this problem. Now, if probability of A is 0.5, and we know the intersection is 0.2, what's in this moon here? Point what? 3. And what's in this moon for B? Point, what's that? 5, yeah. Now, this is kind of interesting. If you look at all these together, what's left outside those two circles, A and B? What's outside of the union of these? Nothing. There's 0. So the union of these is actually 1.0. So 0.3, 0.2, 0.5. Does that make sense? And then the probability of B with this little thing here, this means not in B. So the way I like to do this is here's B, not in B are these. So that's just going to be 0.3. All right. I'll take that out for a second. 0.3. Now, this one is saying the intersection of not A and B. So here's not A. That's not in A. And 0, but that doesn't do anything. Intersect with B, and that's just going to be 0.5. And those are some problems that we had for today. Helpful? Good. Now, exit out of that, go to the next day 4. We're going to look at conditional probability.